Now we are moving to scheduler, which is a solution for the issues due to the concurrent transactions, which we already studied in the concurrency control. So now we are moving to scheduler. Scheduler is a special DBMS program which is used to order the concurrent transactions for execution. In scheduler, we schedule all the concurrent transactions so that they may not collide with one another or may not overlap with one another. So in this way, there would be no conflict among the concurrent transactions. Adds the execution of database operations to ensure serializability and isolation of transactions. So once the concurrent transactions are scheduled, then the serializability will be ensured and all the transactions will be isolated from one another. To determine the appropriate order, the scheduler bases its actions on concurrency control algorithms such as locking and time stamping. Usually, we use two types of algorithms. The first one is locking, and the second one is time stamping. Both are used for concurrency control. In the locking, we lock all the data items in the database depending upon the requirement. We may lock a single table and we may lock the entire database for a transaction. And due to locking, we may face some deadlocks. So to avoid deadlocks, we also use time stamping mechanism. The scheduler ensures a computer central processing unit is used efficiently, means that the scheduler keeps the tasks in such a way that the CPU is not kept idle or not given some extra load so that it might be used efficiently. And the basic or the simplest way for scheduling is FIFO, first in, first out, without any preemption. Facilitates data isolation to ensure that two transactions do not update the same data element at the same time. With concurrent transactions, the most important thing is to check their type of operation. If a single concurrent transaction, if there are two transactions and any of these two transactions is modifying data or updating data, then that operation may cause an issue. So here we have two transactions, T1 and T2. Let's say we have a database table, and in a database table we have, let's say, a value. So if T1 and T2 both read that value, only read, in that case there would be no conflict. But if in case any of these two transactions write that value, means update that value or insert something in that table, then in that case there would be conflict. Transaction T1 and T2 are executing concurrently over the same data. When they both access the data and at least one is executing a write command, a conflict can occur. So if both are reading, then there would be no issue, and if any of these two is writing, then there would be conflict among these two transactions. Now we are coming towards the algorithm for the concurrency control, that is the locking mechanism. In locking methods, we lock database or database tables or columns inside the database tables, and also we can lock a single field in the database tables. Lock guarantees exclusive use of a data item to a current transaction. If we have more than one transactions and all the transactions are accessing same data in the database, then that data would be accessed by a single transaction and the rest of the transaction would not be allowed to access that data. Means that data item would be locked for that particular transaction. T2 does not have access to a data item that is currently being used by T1. Suppose T1 accessed a data item, then that data item would not be available for any other transactions. Let's say T2 is another transaction, so it would not be able to access that data item used by T1. Transaction acquires a lock prior to data access. The lock is released when the transaction is completed. In the beginning, T1, if needs to access this data item, T1 requests for lock. And if that item is not used by any other transaction, then the lock is granted to T1. And once the T1 completes its operation, after that the lock is released for other transactions. Required to prevent another transaction from reading inconsistent data. The locking mechanism don't allow other transactions to read inconsistent data which is being used by the current transaction. So for locking in DBMS, we have lock manager, which is responsible for assigning and managing the locks used by the transactions. The lock manager assigns locks and releases locks of data item for transactions. Then we have lock granularity, or the levels of locks. We can lock the entire database. We can lock the tables inside a database. Means that we can lock a particular table for a particular transaction. We can lock pages for particular transactions. We can lock rows inside tables for some transactions, and we can also lock field, a small field that is under a single attribute within a single row for a particular transaction. So these are the levels for locking data items or the entire database. So the first one is about database. Here we have a database. It has two tables, table A and table B. Two transactions, T1 and T2, want to use this database at the same time. Means both are concurrent. So what will happen? In the beginning, T1 will put a request for lock. Since this database is now free and there is no lock on it, the lock manager will grant the lock to this T1 and this database would be locked for T2 or any other transaction. At the same time, once this database has been locked, T2 also requests for lock. But since it has been locked, so the T2 must wait until this lock has been released. So T2 will wait for this database to be unlocked. And once T1 completes its operation, this database would be unlocked or the lock will be released by the lock manager, and after that T2 will be given the lock. So Due to the locking mechanism, only one transaction at one time accessed this database. Then we have table level lock. Here we have a table in the database. Table A, transaction 1 T1 requests for lock. The lock has been given, and at the same time T2 also requested, but since this table has been locked, so it must wait until this lock has been released or this table has been unlocked. So once the operation of T1 is completed, after that the table is unlocked, and after that the T2 is given the lock, and now here T2 is able to process this database table. These locks are given and released by lock manager. T1 and T2 can access the same database concurrently as long as they use different tables. If there are different tables, they can use, but if they want to access the same table, for that purpose, the locking mechanism must be followed. Can cause issues even if the transaction want to access different parts of the table and would not interfere with each other. Now, in such case, the entire table is locked. It is possible that in this table, T2 wants something to be changed here, and T1 wants an operation here. So both are at different locations. So even they are not interfering, but still this lock is implemented on the entire database table. So it is not suitable for multi-user database management systems. Then we have page level lock. An entire disk page is locked. A table can span several pages, and each page can contain several rows of one or more tables. Here we have a single table, it has two pages. So transaction 1 is given lock for page 1, and at the same time transaction 2 also requested this page, but since this has been locked, so it must wait. So at the same time transaction 2 also needs another page, so it requested for another page, and the another page has been given to transaction 2. After that we have row level lock. In row level lock, the rows inside tables are locked for transactions. Concurrent transactions can access different rows of the same table even if the rows are located on the same page. Here we have two pages, page 1 and page 2 inside table A. Now T1 needs to update row 1 which is inside page 1, and T2 needs to update row 2 which is also inside page 1. So what happens here, the row number 1 is locked for T1 and row number 2 is locked for T2. It has a high overhead because the level of lock is at minor level, and this would put extra load on the DBMS, but it improves the data availability because for each lock different or separate for each row separate locks are used. Then we have field level lock. Field level lock allows concurrent transactions to access the same row as long as they require the use of different fields within that row. Suppose here we have some rows in a table. T1 wants to access an attribute value in that row, and T2 wants to access another attribute value in that row. So here one lock will be given for T1 and one lock will be given for T2 on these two separate values. So this one is more flexible lock but requires an extremely high level of overhead. This would put extra load on the DBMS because the level of lock is at the bottom and processing it would take some extra time. Due to locks, we may face deadlocks. A deadlock is a condition that occurs when two transactions wait for each other to unlock data. Here we have an example. Suppose we have two transactions T1 and T2, and T1 needs data item X, and after X, Y to complete its operation. We can write it like this. Here we have T1, T needs X and then Y. T2 needs Y and then X. These X and Y are fields in the database. These could be some rows or some values under the attributes in particular rows. So each gets the first piece of data but then waits to get the second, which the other transaction is already holding. Now here X is given to T1 and Y is given to T2. T1 is waiting for Y, which has been locked by T2, and T2 is waiting for X, which has been locked by T1. So in this case, both are waiting for one another and they are not releasing their own captured values, and such situation is known as deadlock. Possible only if one of the transactions want to obtain an exclusive lock on a data item. Actually, this type of lock is known as exclusive lock. These locks are not shared with other transactions. We have one another option of shared locks in which multiple transactions share a particular lock. In that case, deadlocks don't occur. Here we have the example. T1 requested to lock X since this X is free from any lock. So the lock manager replied with OK and unlocked X for T1. And at the same time, the data item Y is also unlocked. Then T2 requested Y, it's free. The lock manager locked it for T2. And after that, T1 requested to lock Y, but since it has been locked by T2, so it must wait. Similarly, T2 requested for Y, which has been locked by T1, and now it must wait. So here we have an infinite condition of wait for both the transactions. Both need X and Y to complete their operation, and both are holding these values too. Concurrency control with time stamping method. Now to control these locks or these deadlocks due to locking mechanism, the exclusive locking mechanism, we have another approach, that is time stamping. Assign a global unique timestamp to each transaction. Each transaction is given a time or timestamp. All database operations within the same transaction must have the same time stamp. So actually time slots are made and each transaction is given a time slot to lock in item. Once that time slot has been expired, after that the lock will be released automatically, and if any change is made before the commit, that change would be reverted or rollbacked. Produces an explicit order in which transactions are submitted to the DBMS. Here, these timestamps are considered as unique, ensures that no equal timestamp values can exist. Then we have two terminologies, wait die and wait wound schemes. In wait die, the older transaction waits and the younger transaction is rollbacked and rescheduled. It is actually due to this thing here. The older transaction waits and the younger transaction is rollbacked. Now let's say T1 is older, so it must wait for Y, but the younger T2 will withdraw Y for this T1. So it will not hold that lock forever. It must sacrifice. Then in second case, the wait wound, older transaction rolls back the younger transaction and reschedules it. What happens here? The older transaction T1 rolls back T2 and reschedules T2. In the situation where a transaction requests multiple locks, each lock request has an associated timeout value. The locks are given time slots, so these time slots expire. So if the time period for a lock has been expired, that lock would be released automatically. If the lock is not granted before the timeout expire, the transaction is rollbacked. Here, in wait situation, if Y is waiting for a lock and that time period has been expired, so that would be rollbacked automatically. Here we have wait die and wait wound scenario. Transaction requesting lock T1 is requesting this item and T2 is requesting something. Here the locks are given to T2, this one item, and T1 is given lock on this item. Now in wait die scheme, if T1 is requesting this thing and T2 is given this thing, then T1 waits until T2 is completed and T2 releases its lock. So here T1 is waiting and T2 completes its task. And wait wound scheme, T1 preempts rollbacks T2. Means if some changes are made by T2 and those changes are not committed, so those changes would roll back, and this thing is done by T1. T2 is rescheduled using the same time stamp. So after that the resource is given to T1 and T2 is rescheduled. In case of wait die, here T2 dies rollbacks automatically by itself. T2 is rescheduled using the same timestamp. And in wait wound scheme, T2 waits until T1 is completed and T1 releases its lock by itself. Or about the wait die and wait wound.